There we go. So first of all, thank you, Frank, for giving me this opportunity. I've actually been looking forward to this very much. Yeah, so as Frank said, my name is Andreas. I am a third-year PhD student in the play group, same year as Will was. And today I'll be taking you all through generative adversarial networks, and then also the adversarial learned inference, let's say the extension of GANs. And as Frank said, I've become now the de facto expert on this. I don't know actually really how that happened, but you know, that's just sort of happens when you start to do research. You end up in this one avenue, and here we are. But they're quite exciting. I think they're super fun, and they can do a lot of stuff. And hopefully, after today, you'll all see the benefits and the power of what this framework can do, and maybe you can use it as well. So, just to put it in context to what you guys have done before. You've usually been like working with methods which required you guys to evaluate some sort of density, like whether it's the joint, whether it's the marginal. It typically requires you to evaluate some sort of like one of those or some conditional density. And for the purpose of this slides, and as you've probably known before, we'll consider Y to be the set of observable variables, and we'll consider X here to be the set of latent variables. But otherwise, we'll just say that V is the variable that is the joint to the union of the two sets. So we'll just consider V as all the random variables. So this could be a scalar value, or it could be a vector of random variables. So if you consider the case of generative modeling, where we might have a density that's parameterized by theta, we'd say we want to approximate this density to some target density, which we cannot evaluate, and we can maybe only sample from it. So this is where we'd have observable data from this. And what you looked at last time with Will is that you could use normalizing flows, for instance, to match these two densities, but that required that we would be able to evaluate peak theta of Y, or rather it enables us to evaluate peak theta of Y through invertible functions and the change of variable formula. Another way we could try to do generative modeling is to maximize the elbow, which I'm sure you've seen numerous times in the course. Where you put a lower bound on the model evidence, and then you maximize this right-hand side. And in this case, you need to be able to evaluate both this Q conditional density, which is typically what you say is your posterior distribution. So the elbow can help you with both inference and generative modeling, but just to sort of make that clear here. And you'd also have to evaluate the joint here, right? Where the joint density is factored up as the likelihood and multiplied by some prior distribution that you have on your latent variables. And you might have some MCMC method where you might be able to evaluate a density like this joint, but it might be difficult to sample from it directly. But this is probably a less common situation, but you could use something like rejection sampling. And in the case of inference, right, you're trying to learn this posterior distribution approximately equal to the true posterior. And here you'd use like maximizing the elbow. You could use something like inference compilation, which you've also seen, where we have the expectation of the minus log Q phi. Again, you need to evaluate Q phi. And you have a host of MCMC methods, which typically requires to evaluate the likelihood function or a joint density, so the non-normalized posterior, and you have self-normalized portion sampling. Right? But the problem with all this, or rather, so we say, the restriction is you need to evaluate all these densities, and that puts some sort of restriction to the space of functions that you can actually use to approximate these unknown densities. So what we're going to talk about today is we're looking at these generative adversarial networks and the extension adversarially learned inference. And what's really cool about these is that you don't have to evaluate any densities ever. Right? And they have been proven to be incredibly powerful, especially for generative modeling. That's what they were developed for. So most work has gone in that direction. And as you can see here, this is an image that shows a very popular GAN, which has produced like near photorealistic images. And Frank's got his hand up, right? What do you think?
Indeed. So like you're selling it as cool that you don't have to evaluate any densities. Isn't that like it's a double-edged sword? That means you also don't have access to any of the densities that you might want to use in downstream tasks.
Yes. So we will, of course, get to that, I think, later on as well. But you're absolutely right. So, of course, if you want to evaluate, let's say, the likelihood of some sort of like observable data point, you can't reason about how likely that is, right? You can only sample from these methods. And we'll make that clear again later on as we go on. So I'll keep remind you that we can only sample from these models. Did that answer your question? Or comment, whatever.
Yeah,
sweet.
Yeah.
So of course there's downsides, and I'm going to focus mostly on the positives, but of course another cause is that since you don't have an explicit density, what seems to be the case training these models is they can be notoriously difficult to train. So I'm saying this now, and I won't get back to it because it makes it sound less cool. But they can do amazing things when you get them to work properly, and this image I think represents that quite well. Okay. So we'll start off talking about the generative adversarial networks, or GANs, before going into the adversarial learned inference. And the reason for that is the extension and the transition is super straightforward once we know how GANs work. So we're going to spend a lot of time doing just generative modeling. And if you're thinking about when does inference come into this, it will be straightforward when we get there. So before we go into the details of GANs, let's think a bit about why care about GANs and maybe generative modeling in general from a super high level brief discussion here. And this is also going to address some of Frank's concerns. Because, well, first of all, if the only thing we can do is sample from these models, like why do we care about this? You could always just say, let's go out in the world and just sample more data from wherever you got it from in the first place. But there might be some cases where it's prohibited to do so. You might have safety reasons, monetary costs, computational costs if you have a simulator, where you might want to learn a generative model that you can then use while you say, for instance, wait for real data, and use that as an approximation to the real data density. And then you have maybe an approximate solution to your original problem, which will save you time, right? So generative modeling, I think, is worthwhile thinking about, but this question does come up every once in a while, and I do the same thing with with people in the play group, that we talk about this every once in a while. And arguably, inference could be the more interesting part of it, but we'll get there. So, what are GANs? As the name implies, they are generative models. The aim is, as it was stated earlier, to learn this p theta to be approximately equal to some real data generating distribution, which we denote p real. Generally, we're going to be saying, and we need to remember this basically always, this p theta is intractable, can't be evaluated, it just sort of exists. But the nice thing about GANs is that we can efficiently sample from it, because it's parameterized by neural networks, and they're quite fast if you just want to produce a single sample. And they're easily extendable to do inference with them. And by starting off with just GANs, it'll be super easy to understand the inference part of this when later on. So the generator framework consists originally on just two different components. We have the so-called generator, which will denote g theta, and the generator conceptually is trying to fool a so-called adversary. And it does so by trying to generate real data, or realistic data. So we say that the generator is a mapping from this space Z to the space V, and it needs to be differentiable, of course, with respect to theta. We need to train this somehow, and as you can imagine, we might use gradient set. And this set from this set space is a random vector. So as you can imagine, because the random vector is random, the output of the generator will also be random.
Have you done something beautiful here and actually used V like on purpose to hint that it's going to be the joint distribution later?
Yes.
Nice.
I try to stay consistent. It might have slipped every once in a while, but I try to say that just to use that notation. You typically might think about X and Y's, but right now, from the generative perspective, we don't really care about latents and observables. We just care about random variables. So that's why I use V here. So this could easily still be seen as splitting this up, but you see that later on exactly how we do that. But now we just look at V as just random vector or random variable.
Very pretty. I like it. Yeah.
Yeah, and so the adversary, and if you've known about GANs before, is typically referred to as a critic or a discriminator. Is something that tries to distinguish between real and fake data. Right. So you can think of this as, the generator fools the adversary that tries to distinguish between real and fake. And you can think of the adversary as giving a hint to the generator if it's doing a good job or not. Okay. And so more, yeah.
Like, this is sort of related, like going back to that the likelihood is intractable here. Can you think about this in some way, like the adversary being able to learn like a very, very, very crude approximation of the likelihood? Because you're sort of telling it to learn whether the sample is in the data distribution or outside the data distribution, right? So it's sort of like saying zero likelihood, finite likelihood, zero likelihood, finite likelihood. Is that a way of thinking about this? Does that get you anywhere?
It's getting close. It's not quite right. It's close though. It's going to tell you like the ratio between densities. That's what actually comes out of it. So that way, it's going to give you like a ratio. We see an actual form of this, which will, I think, going to answer your questions. But it's not a. I think it's good intuition. But it's going to tell you more like what's the ratio of being from a real distribution or a fake distribution. It's more like that, which I think still speaks towards what you're actually saying.
Yeah, okay.
But it's not just one density, but it's like a ratio between them. So we'll see exactly what that looks like. So I think that's a good question.
Cool, thanks.
Yeah. So so the adversary is going to map from this space V to some space A. And so far I haven't specified what A is, but it's because A will change depending on the GAN type. So we're going to focus on a particular one in just a second, but just for reference, this output space A depends on the kind of GAN you might be looking at, because there's a whole host of these. All right, and both of these, the generator and the adversary, are parameterized by neural networks. So we can train these using something like gradient descent. Okay, so now let's talk about this implicit distribution that the generator actually produces. And we'll go over the next few slides to setting up some basic fundamentals, like how we should look at this, how we can sort of train this, how we can estimate various expectations using this GAN framework. But first of all, this random vector set here, right, is distributed according to some base distribution, which we denote mu. And so the generator will induce this generally intractable distribution over its output, right? Because you map from set to E. But it's this distribution that we don't know that is defined with this output, which we denote p theta. So it's implicit, we can't evaluate it, but it exists. Now, to tie in with what Will talked about last time, if the generator was invertible, we could use the change of variable formula, and then we would actually have a normalizing flow. So in that sense, it relates heavily to what we've sort of seen before. And the next slide will also tie in the reparameterization trick. But the point is, GANs, we don't have invertible generators. We don't place any such restrictions on our models, right? It just needs to be differentiable. And probably some other details, but this is like the overall sort of takeaway here is that we just want to be able to differentiate through it, optimize its parameters. And you could say maybe this allows for more flexibility. We don't have restrictions on the type of models you can use, the type of architectures. And it can also be computationally more efficient than, for instance, normalizing flows. Because the last time, I think I looked at Will's slides briefly, is there are certain trade-offs with normalizing flows. They can be simple and quite efficient, or more complex, but then they might be slow to sample and might be slow to train them. For GANs, you don't have these kind of trade-offs because we don't care about those restrictions. Secondly, GAN's going to have to involve estimating expectations and also their gradients. So how do we do that? We have faced a similar problem that you've seen before. So you might have expectations that look like this in the following form, right? Where you have an expectation, where the expectation itself is with respect to our model that is parameterized. And we have some objective function that's called f, which also depends on our parameters. And simply like using the chain rule, taking the gradient inside the expectation, we end up with these two terms, right? So let's use this. So this here, as you remember, this is easy, and this one is hard. Right. Now you can use this reinforced trick. I don't know if you've talked about that, Frank, at any point, but the reinforced trick allows us to use this this simple identity to actually rewrite the second term as another expectation, which we can then estimate. Now there's two issues with the GANs, and the first one is actually general. There is a high variance in the second term, right? But the second one, which is sort of makes the first one kind of redundant, is that since we cannot evaluate this guy, we can't do this trick anyway. It doesn't help us. So the only thing we can do, what we do to solve this, is to use the reparameterization trench. And if you remember that from Will's lecture last time, if we have some distribution, some random vector set distributed according to mu, so base distribution, if we have a function that maps from set to B, where we have the output, we denote that as a random vector B, then we can estimate then we say that the expectation, or the gradient of the expectation with respect to p theta, is equal to the gradient of the expectation with respect to the base distribution, where we use this function mapping from this base random variable. So we can use this in GAN as well. This is what we will be doing. Okay. So let's get into more of the details of the GANs and the actual framework and how it works. We'll start with a more conceptual introduction that gives us more of a high level before we go on and use a more probabilistic interpretation and a more mathematical approach to understand what they're actually doing. But first of all, GANs are framed as a minimax game where we pivot this adversary against this generator. Like I mentioned before, the generator fools the adversary. And the adversary tries to distinguish real and fake. Now, mathematically, this minimax game is defined entirely by this objective function, which we'll denote H, which depends on this induced density, or it depends on these parameters theta, and it depends on the adversary, and of course the data generating distribution, but we leave that out because it's going to be fixed. It's always going to be there. And generally, the form of H will change on different GANs. We'll be focused on just one of them, but generally this will change if you look at different GAN frameworks. And so what you're trying to solve is equation 2. Quite simply, you're trying to maximize this objective function with respect to phi, and you're trying to minimize with respect to theta. So that's how you say they compete against each other. And what's common to all of these GAN frameworks, regardless of which one you look at, the solution to this equation 2 will leave p theta equal to the real data generating distribution, which means when you sample from p theta, it's as if you're sampling from the real data generating distribution. In practice, we can't solve this obviously analytically. What we do is we alternately optimize first the adversary, then the generator. So you first solve the inner maximization, then you solve the outer minimization. And that's where you get this competing behavior from, right? You alternate, you do first one and then the other. So now we'll tie it into something a bit more concrete. We're going to look at the original GAN objective that was introduced in 2014, and we'll basically just focus on that today. But in this case, the output A becomes this interval 0 to 1. And it means that the adversary will actually become a classifier. Hence the notion of it tries to classify real and fake data. And the objective function looks just like this. So it becomes an expectation with respect to the real data of the log output of the adversary, plus the expectation of with respect to our implicit density, log 1 minus the adversary. And you might realize and recognize that this looks a lot like maximum likelihood actually for classification. And there is a very close connection to that, and we'll see that in a minute. But if you think about it as classifying, what you're really saying here, this first term, is you're trying to classify all the real samples as being belonging to the first, like the class that represents real. And the second term tries to make the adversary classify fake data as being fake. And when you try to minimize this objective function now with respect to the generator, you're saying, fool the adversary. Try to make it as difficult for the adversary as possible to predict the fake data to be fake, which is the same as making the data look as if it's going to be real. Yeah, skip one. Here we go. So there's a visual illustration here of how this works out. So at the bottom here, we have this base distribution. And the arrows represent the mapping done by G. We have here, right? The green line is this implicit density. The data represents the real density, and then we have the adversary. And what happens is that if you consider the base distribution, as you map it through our generator, points that are moved closer together will have a higher density, and points that are more dispersed will have a lower density. And so that's why we get this green line here that represents that green one. Now the adversary is trained to classify whether data is real or fake. So in this direction here, it's classifying data to be real, and this region over here, it's classifying the data to be fake. And in order for us to then train the generator, we need to move this green line in the uphill direction of the adversary, basically moving it towards the real data distribution. So that's like more of a visual representation of what's happening. So when you move the green line, you'd have to update the adversary to make it a new good classifier. And then you have this iterative process.
Sorry, sorry, Andreas. Could you explain a little bit about what that line, the adversary line, is? Like what's the y-axis maybe?
Yeah, so this is the output, right? So you still have x as the one below. So this is just for the adversary. This will be a of x here. So think about this being a sigmoid, basically. That makes sense. So it basically means that the output of the adversary is the probability. So this will be the probability that x is real. Right. So this line here would be 1, and this line here will be 0.
And so, okay, so clearly at the inflection point of that adversary line is where like there's like a shift. There's a mismatch between the green and the dotted line, but there's also a shift, like a mismatch on the left-hand side where it's predicting 1, right?
Yeah, but that's, trying to see, so what's happening here in the sense that we want the adversary to not be able to do such a classification well, right? So of course, in this region, sort of here, right, this region here, it's not quite sure, right? It puts some sort of non-certain probability on it being real or not, which makes sense because the two densities overlap in this image, right? But when you're out here in this region, I'm just going to use a different color here, like this region, right? The density is higher, like some sort of like Gaussian in this case, right? So the green one drops much quicker out there than the black line sort of would give the real data distribution. So the classifier is very certain out here that the data that comes from out here would be the real data. And similarly in the other direction, right? It's very sure that it's not real data. And that's why it's very low. So you have a high probability that it's fake data, and the other direction you have a high probability that it's real data.
Got it.
Can I ask a question here that will maybe help answer Ryan's as well? Which kind of goes back to my original question. Like, if you were to divide the data by the model distribution here, would you basically get that sigmoid curve, more or less?
If you were to divide...
So divide the black dots by green line, would you get blue dotted?
Not quite this close. So what happens is, actually, and it's sort of written there, but just going a bit forward, we're going a bit forward a bit quickly here, but what happens with A is that this will actually, the output of A of X is actually equal to this following ratio. Right, so it's not quite, it's close, but it's not quite. So we jumped a bit, we'll get to that, we'll derive this, that this is going to be happening. So it's very close, but it's the ratio between real and the sum of the two. Because it needs to also be normalizable. So if you think about it, if it was just the ratio, it's not a probability, but this way it is actually a probability.
Awesome, thanks.
right? So before we just get to the algorithm, just for simplicity, and as we would typically like, we like to think about loss functions. But we can define the following two loss functions, where we have one loss for the generator, which is just equal to our objective function. Remember, we wanted to minimize that. And for the adversary, we would just say that is negative the objective function. And all we've done is just turn the maximization into a minimization. But it's just now we can refer to these different loss functions throughout without thinking about maximization. Minimization is just minimizations. And the algorithm is actually very straightforward in essence. It's literally kind of just this. Then there's a whole bunch of kinks and tricks you do in practice, but in essence, what you want to do is to define a set of training iterations that you normally would with new network-based models. Then you're going to define a number of times you want to update the adversary. Remember, the adversary updates was the min and then the max, right? And so before you do minimization on the outer one, we want to solve this problem first. That's why we might take more steps on the adversary to sort of get closer to this maximization point. And all you do is you estimate this adversary loss, you calculate its the gradient, and then you update phi with respect to using that gradient. You use gradient descent or some other optimization scheme like that. Once you're satisfied with the adversary updates, you turn to updating the generator. You estimate the loss of the generator, estimate its calculate the gradient using some sort of optimized autodiff library, and then you update theta along d theta. That is the core of GANs. This is how you would optimize it. And so, are there any questions so far other than what you've had?
Yeah, I guess I have another question about the previous slide. So, like, I guess the schedule of adversary versus generator training is like very data dependent. So, would you want to like, would you typically do something way smarter than this? Like in terms of how well you're, like, just to have an estimate of how well your each one is doing so far and focus more on that.
So in practice, it's
funny you just ask that question.
So in practice, that variable, I think actually that mostly depends on the kind of GAN you're using. So that's why I can't really write it sort of here in this sense as a general algorithm. It very much depends on the kind of GAN. So without going too much into the nitty-gritty details, but for instance, this original GAN suffers very much from vanishing gradients, which is just a problem with the fact that the adversary is effectively has an output. The last activation function is the sigmoid, right? So if you think about the sigmoid, you have gradient phi is like 0 up here, and it's like 0 down here, basically. I'm abusing notation here a bit, right? And that means when you do gradient descent, you know, if you end up too far in these regions at any point with the generator and the real data being too far apart, you'll actually not be able to update your generator. So that means in practice, you want to be careful in the beginning to not update your adversary too much, because it becomes difficult to update your generator. And then maybe later down the line, you might want to sort of tighten that up a bit as you think your generator gets closer to the actual real data distribution, to the point where you're moving more like this region here, right? Because it's better for your gradient signals. There are other GANs that does not suffer from this problem. And in that case, you might want to take more adversary updates every time because you don't have vanishing gradient issues. But then you end up with a computational problem as well, right? That if you take too many adversary updates, you're going to multiply your. Basically, what you consider, right, is that this number here defines like the number of updates you're going to be doing on your generator. But for every time you then do several adversary update steps, it's linear in that number, right? So you're just going to extend your computation linearly with that number. So you kind of want to not keep that too big, because otherwise you won't do anything with your generator in practice. So in practice, there are different considerations to make. So you'd have to look at the particular tables that deal with those ones and see what they basically suggest. In the original GAN, you basically put this equal to, like both of these to be equal to 1, actually. And it works quite well, even still.
Okay.
All right.
Thanks.
Any other questions? Okay, we'll continue. So now we talked about it from more like conceptual perspective. So let's make absolutely clear what it means to treat this as a classifier and why does GANs actually work. So we'll take a probabilistic interpretation. We'll rederive the objective function for GANs by actually posing the problem of training a classifier, determining whether data is real or fake. And from that, we'll be able to give a new perspective for why GANs in the original form actually works. And then I'll just make a quick relation to other GANs. They have similar interpretations. It's not the same perspective, but it's a different probabilistic perspective, but all GANs tend to have this sort of equivalent way of framing the problem. And it will give you a whole new, I think, insight to why GANs actually work. It's not this magical thing where someone just said, let's fool an adversary and do something with the generator. It actually makes sense. So like we saw before, right, this looks a lot like this maximum likelihood for a classification problem. And there is indeed a connection to that. So if you want to pose the problem at first, not thinking about GANs, but just wanted to train a classifier, we'll consider the tuple of C and B, two random variables, such that we define this conditional density over our variables, which is equal to p theta if C is equal to 1, and is equal to the real data distribution if C is equal to 1, before it was equal to 0. So basically all we've done now is we've labeled our data that either the data comes from the fake distribution or it comes from the real distribution. We define PV without any sort of subscripts as just the mixture of the two. Because we need this later on, but otherwise we won't refer to it again. But we do need this in the next slide. And the key here, the only thing we've done is we've now just labeled the data. We assume we know where the data comes from. Now the problem we set out to solve is we want to learn the class posterior. So imagine we now want this fellow here, P phi, of the class label given the data. And we want to make that approximately equal to this true posterior over the class labels. And immediately, to make it clear, we will actually substitute, or at least make this connection, that this P phi is actually the adversary. Because that is what it will be. We can just denote that as the adversary. Because remember, the adversary was defined as mapping from V to this range. So we can treat it as a probability. So one of the many ways we could train this thing, or try to make sure that these posteriors are equal, is to minimize the Kullback-Leibler divergence, which you've seen many times in this course, I believe. So let's consider the following loss function. We take an expectation with respect to all of our data, right? So this is the mixture of all of our the data we have. That means both the real data distribution and our generator P theta. And then we consider this expectation of this Kullback-Leibler divergence between the true posterior, class posterior, and the parameterized class posterior, our adversary. If you write this out, and you leave constant terms that does not depend on phi, you get minus the probability that the data point is fake, times the expectation with respect to our data generative, or the generator induced density of log 1 minus our adversary. And then you have minus the probability that a data point is real with the expectation, times the expectation with respect to the real data distribution, log adversary, plus this constant terms. And now, just for simplicity, I make alpha equal to these probabilities just to unclutter it a little bit. And the point here, first of all, we fix theta. We don't care about the generator so far. We only think about what does it mean to have an adversary. And the interesting thing is that if we set alpha equal to 1/2, and we drop those constant terms, we see that minus this loss squiggle with respect to phi is in fact equal to 1/2 of our objective function that we defined earlier. So you can see here there's a direct connection between those two objectives. we can frame maximum likelihood framed in terms of where we try to find the class posterior with the KL to actually recover our objective function. And this half constant does not change the optimum. So really what we've done is that we've said minimizing L squiggle, or this real L, is equivalent to maximizing this objective function H, or minimizing this L at best that we defined earlier. And this is exactly what we wanted to show. And again, we only consider minimizing this KL with respect to phi, so we don't introduce generator here just yet. So this is the way we can sort of look at what does it mean to have an adversary. What are we doing with the adversary? Because they're equivalent problems. So now we need to think about how this will eventually lead to the effect it has on training the generator. So we will now go to the next point where we will consider having an optimal adversary because it solves that inner maximization problem. Right? And so again, we fix theta, but to find the form of the optimal adversary, it doesn't really help us much to think about these phis because it's a neural network. Finding the optimal phi is completely sort of infeasible, and you know we'll use gradient descent to get to that point. But we could consider this L adversary as a functional operator with respect to the function that is the adversary. So instead of thinking about the optimal parameters, we want to find the function that actually solves our problem. So now we just recast the problem into finding the optimal adversary A star as the argmin over all adversaries of this loss as a function of the adversary. And if you use calculus of variations and you take the functional derivative, you end up with this equation here. And solving for this optimal function, you end up with the optimal adversary taking this form, which is what I showed earlier. I think, Berend, for your question. So this is how we end up seeing that the functional form of the optimal adversary becomes this ratio of the real data distribution over the sum of the real data and our induced density. All right. So now we know what it looks like. And of course, now if we then assume that the adversary is parameterized by phi, if that is expressive enough, then the optimal set of parameters must necessarily satisfy that the adversary with the optimal parameters is equal to this optimal adversary that we found the form for before. And if you plug that back into our objective function, we get the following result, where the loss of the adversary with the optimal adversary parameters is the expectation of these log, the expectation with respect to our generator induced density of log p theta over p theta plus p real. This is actually just, this here is equal to 1 minus a, right? And then we have another term here, which is just log a. Right? This here is log 1 minus a, and this here is log a. Okay. So if you've looked at a lot of divergences, which you probably haven't, but if you have, we can recognize this as actually being up to a constant factor, and scaling factor and a constant is equal to the tension-channel divergence. This is another divergence. There's a whole host of these silly divergences that has different properties, but this is another divergence, right? Which takes the following form. So minus L adversary, which is equal to our objective function with the optimal adversary, is equal to 2 times the Jensen-Channel divergence minus this constant factor. And again, it's just a scaling and basically a shift. So again, we don't change the optimum, but we'll see why this is a very nice result in just a slide from now. And the bottom line is just shows you what the Jensen-Channel divergence actually looks like. And you might recognize these two as the KL between P1 and this function M. And this here is the KL P2 of M. If you want to work this out, where M is this is the average density of the two. So the Jensen-Channel divergence measures how different P1 and P2 is, and then up here what we have is the Jensen-Channel divergence measures the difference between P real and P theta. So now it makes sense also from a different perspective that not only is the adversary as a classifier, but using it actually gives you a value that represents the divergence between your data generated distribution and your generated induced distribution. So the adversary will give you a signal for how good your distribution actually is. So now we can look at what then when we update the generator, right? Because what we would do in practice, what we'd assume when we update it is that we have an optimal adversary. Right? That's an assumption. So we know the solution here with an optimal adversary. Now we just remove and use H tilde to say we don't care about the adversary. We just assume it's always optimal. So this is now just a function theta, the generator. And now we want to solve the problem of finding the optimal generator's parameters, which minimizes this guy here. And it should be clear that the set of optimal adversary and the optimal generator parameters solves this original the original GAN problem. So just to reiterate, we assume the inner maximization is solved from now on. Look at this generator. So what we do in practice with this assumption is that once we've updated the adversary, we will literally just take the gradient with respect to our objective function with respect to theta, which takes the following form, right? And then we will do an update to theta using this gradient. And now we need to be very careful, because what we do in practice is that every time you have now updated the adversary, where we assume the adversary is optimal, if you update the generator, you immediately need to go back and re-update the adversary. Because once you've changed the generator, the old adversary is not optimal anymore. That's why we would always just do one generator update, but might do several adversary updates. It works because the adversary is the inner optimization problem, but the generator is the outer one. Okay. But this is why this is so nice that we found that we had the Jensen channel divergence before, because remember, the optimal adversary gave us this Jensen channel divergence, which means that taking gradient descent steps along the gradient g theta is equivalent to minimizing the Jensen channel divergence. And what we know from divergences is that when it's 0, that is true if and only if the two densities are equal to each other. Okay. So when we minimize this Jensen channel divergence, and if we can get that to its absolute minimum, again, the scaling and the constant doesn't matter, we're just shifting the minimum and how much it's sort of scaled. We know that we will get the real data generating distribution induced by our, it was going to be equal to the density induced by our generator. So I think this is a super nice result, and I think it really sort of clarifies and makes it sort of clear why GANs actually work. And the interesting thing is that this property is the same for almost all different GANs. So it's a different divergence, but it's still going to be some sort of divergence or a measure between densities of some form. So an optimal adversary will lead you to something like this. And then when you have that, you know that updating the generator will in fact help you or be equivalent to minimizing that sort of measure that tells you the difference between the real and the fake density.
Can I ask a quick question here?
Yes.
Was this already sort of stated in the original GAN paper, or was this all stuff that people sort of pieced together later, or like?
No, it's stated in there. Yeah, all of this that follows here, it's done. I think the sort of more probabilistic interpretation and the sort of consequence is not as clearly stated, but they do very clearly say that, you know, with an optimal adversary, you get the Jensen channel divergence. Right. Cool. All right, so let's return to the figure before, just to give us now an iterative understanding of how this works out. You see how we actually update these two quantities. So we'll go from figure A to D, and you know, you still have the same situation. You have a base distribution, you have the mapping to this space V. It leads to some sort of P theta here, right? We've got P real here, and then you have the adversary, that's the blue line. So in A, we haven't updated the adversary. So from A to B, you update the adversary. you get that A is equal to P real over P real plus P theta. And then in C, you update the generator to move the green line here this direction. And then you re-update the adversary. So you get again a tighter, nicer looking blue line. You re-update the generator back and forth. And in the end, you end up with D, where the green line is right on top of the blue dots. And the adversary is 1/2 everywhere because you cannot distinguish between the two densities anymore. And you're done. Oops, that was too much. Right, so far what we've done, now this basically covers GANs. I think for the purpose of this lecture anyway, I think this is a good introduction and it gives a good understanding of how it works. And what we've done is we've introduced it from this conceptual idea that we have an adversary, tries to distinguish between real and fake. The generator tries to fool the adversary. We've derived then the GAN objective using this more probabilistic approach that I think gave more sort of theoretical insight to why GANs actually work. We've seen how the optimal adversary leads to the denser channel divergence, which then makes sense for why the generator updates actually also work. And then again, to make full circle, different GANs, they're going to look different objective functions, and they will lead to different divergences. But the underlying mechanisms are fundamentally the same. And then if you have any questions, if you have those, you can see this is what you're able to do with them. So this is the StyleGAN 2, and as you can see, these are, I think, 2000 by 2000 resolution images. And you can't tell the difference, right? If these are real photos. Like, you have to look very hard, I think, to realize that. So this just shows the power of what you can actually do with these. And GANs were, as far as I'm aware, I might find another paper that could be wrong, but GANs were the first models that really ended up solving this problem of making high resolution images that look like this. BAEs has since then come along and they are competing now. Now I think 2 years later, so it all moves very fast. But they really start showing that you can actually make these high resolution images look just like this.
Can I ask a question? Maybe a silly question. Like, do people actually how do you say that, sort of crowdsource some people that go through the entire data set and look up if there's anything that remotely looks like this? Like, what's the sort of closest of the original training data that you can find that looks like this? Does it make sense?
Are you saying if you make like a corpus of data generated by these generators?
Yeah, well, yeah, I mean, like, no, so, okay, so this GAN was trained on some data, right? And yeah, I suppose that these images are not in the training data set because otherwise it wouldn't be a very good algorithm. But I'm just wondering, like, it's hard to define a metric for this, but what is the closest image in the data set that sort of looks like these images, right? Like, is there going to be a guy with white hair and a beard in there? And is he going to have, is it only swapping out the background, or is it like how far away is it from the original data?
It's a good question. So actually, I don't remember from this paper, and I don't even know if they have those sort of like images that sort of represent that. Let's say you did some sort of L1 difference between them, or I don't know, some silly k-means, whatever thing you might look at and see like what sort of images are like close to this thing, something like that. Some GAN papers do that, and it is known that GANs tend to actually not be too good at diversifying. So I think your intuition that they can sometimes overfit is definitely valid, and I think this happens. But I can't speak to like how bad it actually is, and I can't also speak to like is it better or worse than, let's say, VAE methods, for instance. Like I'm not quite sure on that. It's a very good question. I could imagine that many of these papers sort of kind of sweep that under the rug a bit, like you maybe don't want to emphasize it too much, right?
I mean, it's a lot of work for like something that may harm you. So I can see why they definitely didn't put that in the original papers, but maybe somebody else after like actually looked at these examples. And
yeah. It's a good. I haven't seen. I mean, I know there is a lot of follow-up work that looks at like different GANs and like look at like what are they doing and sort of goes and asks those kind of questions. And this doesn't speak exactly to what you're saying, but like for instance, some of these works that came afterwards looked at like how easy is it even to reproduce these results, and it's almost impossible basically, which speaks to the fact these are very difficult to train. I think this thing here trains, I think it takes several months on a single GPU. Like this is NVIDIA stuff, right? They just massively scale this up and it's like ridiculous. Like it takes a very long time to get to this, right? And you know, you may have to do this multiple times, several seeds, and find the best one. And I have heard about work that suggested that, you know, this is almost impossible to reproduce on your own. You can make good results, but not those that are that, I mean, they are kind of cherry picked over like several different ones like that. And I think there's also other work that seems to suggest that even, you know, everyone will try to promote their own GAN model and the type of GAN you should use. I think there's also other work that suggests that that may not even be true. Like you might be able to get to the same results across all of those. It's just a matter of like, you know, each paper sort of cherry picks or frames the problem slightly in their favor or something like that. But the bottom line is still like you can do amazing things with them. I think is still the point. And you know, some of these methods might be easier than to, you know, optimize for your particular application. Like maybe this original GAN requires more work because it has vanishing gradient problems. Maybe another GAN, you don't need to worry about that, so they're easier just to get started, right? But it's a good question, it's certainly a valid question too.
Do you have a sense of how big the networks used were to create results like this? So like how many layers?
I think, well, they use this like sort of style notion. So I think they have a style embedding that they call. So it looks, I'll try to draw this very crudely. So they have some sort of, this is a terrible way of drawing layers, but this is layers, different layers. This is styles. And then you have some sort of style, which we call W, that comes out. And I think this is size, there's 8 layers here, I think. And I think the hidden size is 512, I believe. But then they, on top of that, have, I think, 8 upsampling mechanisms in which you sort of induce this in every sort of spot here. And you have some noise you also induce. And I think the number of parameters is, I think, 25 millimeters, something like that, roughly. This doesn't help much. It's
no, that's good.
To draw it. So it's about that. I don't think it's not too bad. Like it's actually quite fast to run. It's just you need a huge batch size, and these images are ridiculous, big. When you start to have channels, it blows up memory-wise. Any other questions? Right, you look very happy with it.
I was trying to help you by looking up the number of parameters in style GAN. That's all.
Ah, right. Yeah, I do recall, like I have used it actually implemented, and I remember seeing it was something like around the 20 normal number of parameters. I'm pretty sure. But I could be wrong. So it's not like GPT, whatever, K, that meta running thingy. It's like billions of parameters. All right, if no more questions, we'll continue on to the next bit, which is going to be how to do inference with this. And I promise you, as you can see, the number of slides.
Do we have time for a two-minute bathroom?
Yes.
Caffeine.
Good point.
Sugar break.
I don't need such things, you know, as I just work.
Right. Let's take 4 minutes. 4:35. See ya. We'll at least capture this slide for posterity.
Be much faster, I promise you.
And we're back.
And we're back. That's just for the recording. Brilliant. So now instead of matching now what we considered before, just like P real and P theta, where we had this real distribution, we like drop those notions of real and fake a bit, and we now just consider let's match joint distributions. Okay, that's I mean, this is on like ultimately the insight we're going to be using here, and you'll see exactly how this works out. So instead of having P real and P theta, we now have this guy here. And wait, I think I missed a slide. That made it difficult. We're going back one slide. I apologize. So here we go. So we've considered different generative modeling, but this will help with the V's and X's and Y's. All right, so it'll be straightforward to extend this to do inference with GANs. Right, and the GANs, for instance, was first proposed by in the paper called Adversarial Inference and bidirectional GANs. And I'm bringing this up because if you are going to read these papers, you should just read this guy. Don't read the other one. I mean, if you want to, great. It's like very measure theoretically heavy. It's super convoluted, and they do the same thing. The first one is.
If the authors of the BiGAN paper ever listen to this, they're now going to hate you, Andreas, just so you know.
That's all right. It doesn't matter. It's interesting from a theoretical perspective. It very much so is. But in terms of accessibility, the other paper sort of takes a more sort of simpler probabilistic approach. And it's going to be what we sort of the notion that we're going to be using here, which is just we're going to change how we just view the GANs working over joints rather than marginals, basically. The other one does more theory, and it's more complicated. So if you like that sort of stuff, read that paper. If you just want to get a quick overview and see how this works out, Ali is the easier paper to read. So for the purpose of inference now, we're going to divide V into the union of these two spaces, Y and X, where a variable Y in squiggle Y is observable, and X in the squiggle X space is the latent variable. And they don't overlap at all. That's the typical way we view this inference problem in terms of how we define the variables. Okay, so now this slide, we drop the notions of P real and P theta as just the two identities. We now instead consider the joints, which are both going to be parameterized. The first joint, P theta, is the one where we will parameterize this conditional Py given X. And in the terminology of latent observables, we'll say this is the likelihood. These are like dummy terms because it really doesn't matter. They're just conditional distributions. But for reference, what you might have done before, consider P theta associated with the likelihood. You consider Q gamma as associated with the posterior distribution over the latent variables given observable variables. And then you have the two marginals Qy and P of X. Now, the trick here to make this work is we say Px is just some prior over latent variables. This is what you've defined and used several times. You've used this with the elbow, so you should be familiar with sort of that notion. But Qy, we set that to be equal to the data generating distribution. Because remember, in GANs, we don't need to evaluate anything, we just need to sample. So we can definitely sample from this guy. This is the empirical distribution over our observable data. And as before, because these are parameterized, they have induced densities, which we also cannot evaluate. So the only thing actually we could evaluate probably is actually P of X, but again, we don't have to evaluate it, but we could if we wanted to. So here's the trick. If the two joints are equal to each other, if they're equal, then we know that the marginal of P theta of our observable value of our observable variables will be equal to Qy. And remember, I just defined this data empirical. Right? So that means when we sample from P theta, we will sample again from the true data distribution represented by the empirical. And similarly now Q gamma of the latent variables is equal to our prior. So this is more of these are sort of trivial results, but these are like actually the insights. Because what we just looked at with GANs is that all they do is that they match distributions, right? So now we can match this fellow with this fellow using GANs like we just did before. All we do is just we would replace this guy with this guy. And similarly, we replace actually P real, and it doesn't matter if it's real or whatever, these are dummy terminologies actually, right? But P real would be replaced with Q gamma. Right? And we can match those two joints using the GAN we just looked at. It's not going to be any difference whatsoever otherwise. So this is the inside. So now we match joints, and now we match these also joints. They were joints before now, but now they factor out in this particular way. So the other difference, and more practically, is now you have two generators. The framework remains the same. So in Alley, what you have is the two generators, gy that maps from x, and gx that maps from y. And I've changed the notation a bit, so the subscript denotes which space the generator maps to. And what's common to both of them, as before, they map from this random vector set to their respective outputs by also taking in a value from the space they're mapping from. These two. And again, they're both parameterized by new networks. Now the adversary is literally the same as before. It's just now we consider this product space of x and y. But remember, right, that V is equal to this product space. That was terrible notation, but whatever, right? That's what we just saw before. So that's what I mean, like, before we looked at V for the original GANs because it's just a joint of x and y. Now we just explicitly divided it up into latent and observable variables. So in this GAN formulation for Alley, the only difference we have is we consider the following objective function, which now depends, of course, P theta still, Q gamma, the adversary, but now the expectation is written out explicitly a sample x and y from this joint log adversary plus sample x and y from this Q joint, and this is supposed to be Q, and 1 minus this adversary. So in this formulation, if you want to, we've sort of defined this to be real, and we've defined this to be fake. But if you think about it, it doesn't matter. It didn't have any meaning before. It's just it makes sense to say real and fake. But now it just doesn't matter. But otherwise, the terminology would otherwise be the same. So an illustrative sort of way of showing how this works is that on the right-hand side, the thing about this is the game, is you have this guy together with this guy that jointly tries to beat the adversary. So the adversary tries to distinguish between them, and the two generators try to fool the adversary, and to do that, they need to be equal to each other. That way, the adversary can't distinguish them from one another. So in practice, what you do, you would first sample y from this Q of y, push it through the generator, right? Which then makes it a sample x hat from Qx given y. It gives you this tuple. You can pass that into the adversary. And similarly, from the other direction, you start from P of x, pass it through the generator for y, which gives you this y tilde from Py given x, which gives you this tuple y tilde and x. And when they're equal to each other, I need to see what my next slide is. Here we go. This is for cognitive programming. We'll go back one more slide. But the point is, in this formulation, Qy given x will become, by almost definition, the posterior distribution once they're equal.
Don't you mean x given y? Your ultimate point.
My ultimate point was wrong.
But you worked all the way to the very end, and yeah.
You know, really what happened is I just made this implicit redefinition, right? So now, you know.
Exactly, fine, yeah, we understand, yeah.
Yeah, good. Anyway, this will be sort of by definition of our problem, the posterior. the thing is, if we go back just 1 or 2 slides here, since this is just a prior that we consider that sort of meaningless. We might need to do some sort of encoding of the space that we would like to have. But this is the data distribution. These 2 marginals is sort of what we would choose, so they're sort of fixed. But these 2 conditional identities are completely free, right? So we know that there is not one joint distribution that solves the problem of being able to be marginalized out. So there's several joint distributions that solve the same problem. So we could have several different kinds of conditionals here, so that these 2 joint distributions are equal to each other. So we don't encode any meaning into our latent variables in this framework, right? There's sort of a freedom of however way our GAN wants to sort of treat these latent variables, it can do so. It doesn't really matter. All it needs to do is to be able to map from the latent into our observable variables. And then it just needs to be able to go from observable variables into those latents. And there could be many ways of doing so, right? So from this perspective, you might argue that doing inference may not be so interesting because you don't know anything about it. But that's where, if you use it with probabilistic programming, we might actually start to make a difference, how we interpret all this. And finally, here we are. So if you were to use ALI for probabilistic to perform inference in the context of probabilistic programming, we would instead consider the fixed joint PXY, which is defined by the program, which you've seen now several times. This is what the program does. We would then identify the latent variables and the observed variables using the sample and observed statements, and then we would train using ALI this joint, so the same sort of Q joint, to be equal and approximate this joint distribution. But now we've had a fixed joint distribution, right? So it's one joint distribution, so that's sort of unique. So we have only one joint here, and that fixes this posterior if they're equal to each other, which means that we only need to learn this guy. And so by defining again this QY as being equal to PY, and again, we can always sample from this, but just run the program and just sample the Ys. Then we will have learned the posterior distribution, Q gamma, under our joint distribution defined by the program, right? And you retain all interpretability of those latent variables because they're defined by the program. There's no freedom in what those latent variables do because they're fixed in the program. So that's how you can use ALI and therefore GANs together with probabilistic programming, and you retain all the interpretability, which in the sort of original ALI framework, you lose all of that. And just to show you some quick, less impressive examples, I guess, from ALI, of using that for doing inference. This slide here shows a grid of images where the what is it called? The odd columns are sampled from P of Y, so the data. And the other line here, I don't know how to write this nicely, but basically what you do is that you take the sample Y, that's what described it down here. You sample Y from the data distribution, then you sample the latent variables throughout posterior, and you resample Y hat through the model P theta. So, there might be some noise in this because these are defined as identities. There's going to be noise associated with it, but maybe it's easy to write it like that. Maybe this will help. So this will be Y, this will be Y hat, Y, Y hat, Y hat. Right? Where you first go from Y, get the latent variables, and then get back Y hat, going through all of our models. And these models here that have been used are back from 17, so they're 2 years older than the ones from style GANs, so they don't work as well. There's also not as much work in inference with GANs, so it's not too surprising these don't work so well, but this might be an example of when GANs aren't amazing. But as you can see, it does capture something, right? You can see the left one here is the real image, and clearly the right one retains some sort of representation of the first image and produces a new image. Right? They clearly seem to be correlated and related to one another, which is kind of what you'd expect if inference were to work in this context. Right? You would induce noise over the even columns, but I mean, I guess you'd hope that the images look kind of sort of better, but I mean, they're not that bad, I think, actually. I think they're doing a pretty decent job, except for one of these where you seem to be like swapping out their hats with like, I don't know, dog poo or something. But otherwise, I think it does pretty well. Yeah, that was it. So thank you. I think that's about on time too.
Spectacular. Yeah. Thank you so much, Andres.
Pleasure. Do you have any questions in the end?
Time for some questions, and then we can all feel good about having made it through this enormous journey together. I have a question. Where did the normalization constant go?
Which normalization constant in which one?
Well, you know, anytime we're characterizing a posterior distribution or, you know,
Yep.
building some sort of amortized inference artifact, there's like, we have to, you know, with variational inference, we sidestep having to estimate the normalization constant by, you know, forming an auxiliary objective and observing that a bound becomes tight when something, you know, happens the way we want it to. And basically we sidestep it by running a very long optimization procedure in some sense. Right?
Mm-hmm.
How does it get sidestepped here?
So I guess maybe this, if I understand your question correctly, like you don't worry about the normalization constant in that you basically directly define the posterior distribution as a model itself. So you just have a density that conditions on the, in this case, the observable variables, and that defines the density of its output, which is then conditioned on that.
Well, but we can only sample from Q.
You can only sample from it. You can only sample because you can't evaluate any of this. So that's why you don't. Yeah. So you don't need to.
That's how you sidestep it, right? Because you can't evaluate it, which means you've never actually estimated the constant that you would be required to have in order to.
Yeah. Like in the sense of how it sort of, maybe if you want to see like how it, if you understand like how it appear, I guess, is that it appears by being defined as part of the problem, like it's sort of made implicit as you sample from that margin that you would otherwise use to normalize with. So it appears there, but it appears in the sense that you're sampling from where you don't have to evaluate the, because you don't treat it as a normalization constant. It's just that the marginal that you would use as a normalization constant appears as part of the sort of sampling procedure. Yep. And therefore leave it kind of implicit.
Yeah, no, it's a screwball question, but it's something interesting to think about.
Yeah, for sure.
And in this particular case, because we're only messing around with gamma, we don't need to differentiate through the model if we were to use Ali for Prob Prog inference, or do we need to differentiate through the model?
You don't need to differentiate through the model. You only need to differentiate through the adversary. So the model is actually only used to train the adversary, but you only do that by taking samples from the model. But it's not like the models themselves somehow sort of wraps up the parameters in the adversary, if that makes sense. So therefore, you don't need to worry about differentiating through the model whatsoever.
So why hasn't this been done?
Well, it has sort of been done by me actually, but it didn't go that well, and I guess it was for another class, not yours. And but the biggest problem actually, if you want to think about using Prob Prog, is if you're thinking about hobbles, it becomes much more difficult to think about because you need some way to have variable size spaces. How do you make that work nicely with like an adversary so that it sort of stays consistent? You need to make the adversary at least using like LSTMs, and I think there's a lot of practical considerations that would have to be done to make it work nicely because of that.
Just because of the size of the space of X.
Yes, right, and I think
elements that are different sizes.
Yeah, and I'm not sure even you might need the adversary, right, because it takes as input a certain set of random variables, and I think to make the adversary sort of treat the input space consistently, you need to somehow make it aware of what variables with addresses it needs to take. So you would need to do something like a PyProp with modules associated with different addresses, kind of thing that attaches onto the adversary and stuff like that. Yeah, so I think there's a lot of considerations to make it work there, but I think it could. I don't think there's any reason why you couldn't. The biggest problem, actually, I think, now I think about it, is the discrete variables. We haven't talked about this, but if you've noticed, we talk about differentiability, and that sort of is everywhere, but you can't use reinforce. Right. So, the only way you can do reinforce is you have to make some parts of the generator for the discrete variables actually evaluatable. So you have to actually do a mix of like both worlds. You can train evaluatable densities with GANs. There's no problem with that. But because you can just use the adversary to weight it when you do reinforce. I haven't added that here whatsoever, but you could do that. But you do need to use something like reinforce and have evaluatable densities for the discrete variables. And then you might have a complete generator for continuous ones. So you would need to consider that as well. So I think it's possible to do. It's just, I don't know why it hasn't been done otherwise. I think it's a software engineering nightmare.
And you can't make prefaces, right? You can already make prefaces.
Yeah, so who would care? Isn't that the problem? But it's a good project. Next year. Project next year.
We'll put this lecture first next year. That'll help.
We definitely should.
Yeah.
Can I ask a question?
No.
I'm just waiting for a good moment to interject here. Anyway, Andreas, could you go back to that slide where you have like the diagram of how you do? Yeah, this one. Yeah. So, basically what you're doing here, right? Like on the left and on the right, the gy of x and the gx of y, they are deterministic transformations, right? So it seems that like the conditional variable generation that has a tilde and a hat in both cases, or in the respective cases, you're not actually drawing that sample, right? Like you're transforming it from the other one. Is that correct? Or
what's the difference?
Yeah, so I was hoping no one would actually ask this question because you're technically right here. Now, let me just, before we consider this figure, we should write in this figure, but just, so here you're happy, right? Because here we add the random vector into this, right? Mm-hmm. So here we the generator, and I've overloaded the notation here, so we ran out of time a little bit when I did this. But anyway, technically here, right, there should be a set and a set here too, right? You're right in the original again, this is the image, and there's no additionally induced randomness once you condition on X. So given X, it is a deterministic mapping, so you have a delta function on top of it, so you get a delta distribution, delta derived distribution. There's nothing wrong with that, like Frank said, it's totally fine. It's just you don't have that noise if you would like to have noise in it. But the remedy, and this is what many other papers that use it anyway, they do consider just like inducing noise throughout the model. And actually, if you think about it, many generators, I mean, a lot of it is using vision, right? So instead of framing it sort of like this with a random vector that gets put through the generator, they sort of just talk about the architecture and then they say we add noise because it's good for learning. Kind of, that's the argument of it. But really, when you add noise through the architecture at different layers, you could always view that as having some base distribution and this random vector set, which is all the random noise you induce at any point throughout the data generating procedure in the generator. And then you just have that one mapping that takes the noise and produces some output. Always view it like that. So I think in practice, you do have noise in there, but you're right. In this figure, it does look like it is delta distribution. I was just hoping no one.
Yeah, no, okay. I mean, like already, I think that the idea of delta distribution sort of answers the question. Like I can see that this is also like a valid way of looking at it. I'm just like, wait, it is different, right? But yeah, okay, thanks. I think that's explained.
It is. Yeah, yeah. Not that I know, not if I'm sure actually, or maybe you know this, Frank, but if you have a delta distribution, it might fix somehow the sort of the possible spacing where you can search for like joint distribution. So it might bind that more so. So you might end up with something where you might enforce something like a slightly cyclic behavior, where you would need some sort of way, because it's all deltas, that you need a mapping from X to Y. And to make this actually work, you might need to be able to go from, the same X produces the same Y, and that Y has to sort of induce the same X again. So you might have these invertible, but I'm not sure whether that's true. I'm just thinking about that right now.
I would trust you more than me in thinking.
All right, you shouldn't. But I'm just thinking, I could imagine that might be true, because I don't know how else you would solve this. Because if one is a delta, you obviously fix everything to that one transition. And then if you're trying to match it the other way, you have to go back. Otherwise, you won't be able to go back and forth. So this might be a way to sort of try to say we're learning generators that are the inverse of one another. If you add noise to it, I don't think they have to be, right? Because you are allowing that flexibility. But it's a good point.
If there are no further questions about Andreas's work, then I think we've reached the frankly sad end. It's been an honor and a privilege to sit in front of a camera and talk to you for an entire term. I know that all of you have put in heroic effort, and I am quite certain that all of you have learned even more than you think that you have during this period of time together. And furthermore, I know that it will serve you very, very well in the future, even if some of you may harbor some doubts about how useful it will be at the current instant in time. So ask Andreas; he'll confirm. Anyway, yeah, I look forward to interacting with you on your final projects as they emerge, and I look forward to hearing from you during the final exam slot, which we announced, and hopefully the weather will clear enough, and Bonnie Henry will let us do something like have a class volleyball game or a little cookout on the beach or something after the presentations or something like that when it's all said and done. It would actually be nice to see you all in person at some point. It'd be kind of crazy. And definitely I look forward to seeing you on campus next year when we're all walking around. So thank you very much. And
thank you, Frank.
Take care. Cheers.
Thanks, Frank.
Thanks, Frank.
Yeah. Thank you all.
Thank you.